when we say curvature, okay, this is an important little caveat that you'll find in some places, or people will kind of stick you with. We're saying that space-time is curved. What does that mean? Well, there's various steps. What is curvature? Curvature is something that we see, let's say, either a line is curved or we see a surface is curved. We intuitively know what that is. That's what curvature means, right? We don't have to define it any further than that. That's what we mean by curvature, something curving around. Now, how about if I spoke about a three-dimensional space being curved? What would that mean? We haven't seen that. We have no conception of that. So you could say that it's the wrong word to use. But what happens is we find that we can define mathematically a three-dimensional space, just like we can define a two-dimensional space. And we can define consistently a geometry in that three-dimensional space, and we can define a curved geometry in the sense that the geodesics of that space will deviate from each other just like they do on the surface of the space. And you're talking about, remember, the 2 dimensions and 3 dimensions, the difference is that the 2 dimensions are embedded in the 3 dimensions. The 3 dimensions, you're talking already intrinsic curvature, not embedded in something else. So that's already an abstraction. It's an analogy. Because purists can say there's no such thing as three-dimensional curved space. Because curvature is something that I see. So I don't see it. So I can write equations which use the same kind of geometry, etc., as a curved surface. Ah, okay, that's so. Some people say don't use the word curvature. And then you have space-time, which is 4-dimensional and it's not embedded in something else. And you're talking about curvature of space-time. So people say, what does that mean? So you just have to know what it means. When you're using the word curvature, like the sun rises. We know the sun doesn't rise, but we know exactly what we mean by saying the sun rises, so we can use it. So you can say space-time is curved because you have these equations. You're like psi double dot over psi is equal to some function, and it has the same form as you would have on a curved surface, and so on. That's what we mean.
So when all these string theorists talk about, higher dimensions, would that mean that those are also are they going to the route that they're all curved?
Well, even when you talk about different dimensions, the bottom line is when we only observe, let's say, 3 dimensions of space and 1 dimension of time, so you have to explain why those dimensions aren't visible. And in the end, there's a question of what do you mean by saying that this is a physical dimension? We measure certain things. It all has to come out. Even if we're talking about 4-dimensional space-time, we don't really measure things in 4-dimensional space-time exactly. We measure something now at this point. So you can call it a point in space-time, but you have to construct a map. You can't really, right? Right, and that's why we'll say that the free-fall world line is a geodesic in space-time, even though when we draw it, it looks curved, because we can't really draw space-time, right? We have to do something else to kind of get a picture of space-time. When we map, when we draw things, just like we mentioned a few lectures ago, the Earth is spherical. The surface is the surface of a sphere. By the way, it's often written as S, like S squared, S2. S2 means a 2-dimensional spherical surface. S3 would be like something that you can't visualize, the equivalent. Now, even in S2, what we're talking about, when you say a spherical surface, any surface, if you cut out the interior of the sphere, you just let like on the globe, you peeled off the upper layer with the paper with the paint, and you left it as a shell, like an orange peel, just peeled all without the orange in it.
Sure. It
still has a thickness. It's not a 2-dimensional surface, it's a 3-dimensional object. So to think of a surface, you have to abstract out a 2-dimensional mathematical space from this 3-dimensional object. So already that's some abstraction. When you talk about curvature, we're talking about the curvature of the 2-dimensional space. There really is no such thing as a 2-dimensional space. We've never seen a 2-dimensional space. We only see 3 dimensions, however thin it is. So there's various levels of abstraction that go into saying curvature. Talking about the curvature of an abstract 2-dimensional space that represents what we see of the thinness, of this 3-dimensional object. And then you would talk about curvature of a 3-dimensional space and then space-time and so on and so forth. So there are various levels of abstraction. That's why there's some people who pedantically will not use the word curvature. Weinberg's book tried to avoid using that. He was against it. Now, if you peel the surface of the globe off onto a piece of paper, of course, as we discussed, you have to cut it in various ways, like the petals of a flower. You have this globe, you have to open it somewhere to spread it flat on a table, and it would, when you unfolded this peeled orange, or the surface of the Earth, it would, kind of split out into something like that, maybe, where you would have to join these things together to wrap it around to make it into a sphere. If it was the globe, then you would have, some piece of the United States here, another piece over here, and countries would be split, and Alaska is very far apart from Siberia or whatever. So it's, you can't represent the geometry of a curved surface by using a flat surface. It's going to err in various ways. Now let's look at another level of curvature, which is a surface. So we have a line and we have a surface. If you have some kind of a curved surface and we're looking at the curvature of the surface, we can do the same thing. We can take a sphere and put it next to the surface and then take the 1 over r, or just a circle. But the surface may be curved like this in this way and curved like that in that way. So you maybe need 2 circles, one for this side and one for that side. So you'll have 2 measures of the curvature. Now, if this is the surface and it has these bumps and grooves and valleys and mountains and so on and so forth, we can take some line drawn on this surface, right, cutting across the valleys and the mountains, and it'll have some kind of a curvature. Now, we could measure the curvature of that line using this method, just putting circles underneath the surface or on top of the surface as need be, and measure it. But we can also measure the curvature of the surface while staying in the surface. Okay, and that's something that's due to Riemann and Gauss, this insight. Can you think of a way to measure the curvature of the surface or of a line drawn on a surface without going outside of the surface? Here, we went outside of the line. We drew, if we had, let's say, this line, we went outside of the line to draw a circle and we found the curvature. Can you do something like that here without going outside the surface?
Do you look at the derivatives?
Derivatives of what?
Basically the gradient.
Of?
Or of the surface.
Okay, question is, are you defining that gradient using a 3-dimensional space in which it's embedded? Or are you defining it just with things that are inside the surface?
I see what you mean.
So one way of doing it, for example, would be to draw a circle around some lump. So we have a surface like this as a mountain, and we go around in the flat plane before the mountain. We draw a circle. And then we find the straightest line that's like a diameter going across, cutting across. Instead of taking the circumference, which is a circle, let's say, we go across a diameter like this to the other side. Okay, so we have this plane, this curved surface, which is, let's say, becomes a plane over here and becomes a hemispherical mountain over here. In the plane before the mountain at the foothills, we draw a circle. We go across over the hill like this. Now, what would happen if it was flat? What would we find? If this was a flat surface rather than a mountain, what would we expect to find?
You just go straight.
Well, how do you know if you're going straight or not straight? If you're in the surface, how do you know maybe it's straight? Maybe you're walking straight. Just like if you're on the surface of the Earth, you don't know that you're walking in a curve around the surface. You're just walking straight.
It's the diameter, the distance, I don't know.
Okay, the diameter. Well, what you can do is take the ratio. You have a circle.
Walk around and walk across.
Right, and walk across and see if the ratio is pi. Now, of course, how do you know that this is a circle without drawing the distance?
That's what I was wondering.
Okay, so there are all kinds of subtleties of how to do this. But basically, one can, if you're on the surface, right, you just take any point, for example, the point at the top of the mountain or any other point, and draw a radial length, and a radial length, and a radial length, the same amount, and connect all those points, because a circle is the locus of all points that are equidistant from some point. So we take all the points that are equidistant from that point, and we connect those points. So we can do that. Right? And then we measure this. We walk around on it, and we measure it with a tape measure as we go around. And we do the same thing. We go up this, well, we don't know if it's up. We're just walking along this way, and we take a tape measure, and we measure. If it's flat, then in theory, this should be a circle. This is the diameter. It's a ratio of pi. If it's not, we know it's not flat. So that's intrinsic curvature. Now, if you looked at that hemispherical mountain, you just draw this curve. That curve alone, you could take and put it into space without the rest of the surface. Question is, does that have a curvature? Now, you could just bend it straight like a string. The string itself, if you're bending it like this, has no curvature. The curve has a curvature, but only because it's embedded in this three-dimensional space,
Right.
or on a two-dimensional surface. What we found is a fourth rank tensor. And the fourth rank tensor, when you contract it down to second rank and so on, it provides equations which lead to gravity. And we call it curvature. Why?